Hi everyone, it is a deep learning project for Repro-VAE scene detection in anime. Our project aims at the problem of scene detection in 2D anime using unsupervised learning. Specifically speaking, we want to detect whether there is a scene change between consecutive frames in the animation. The significance of our project is that the detection of scene boundaries can facilitate a wide range of animation understanding tasks, such as scene classification, cross-anime, scene retrieval, and human-centric storyline construction. The main contribution is that we are trying to solve the problem with unsupervised learning model, which is a huge burden to manually label the whole anime training set while still get the job done. We use variational autoencoder as our unsupervised model. Referring to the work we have done in this project, our work can be attributed to developing a novel approach, which will be emphasized more in the following slides to improve the scene change detection of the baseline model. And for the dataset, we use one Japan animation movie, Kimi no Na wa, as training and validation dataset. Listed here are some basic information. Here comes our overall approach for this task. As we can see in the diagram, there exists a variable autoencoder, also known as VAE. Based on the mechanism of VAE, encoder hopes to generate the distribution of z given x. Reparameterization trick is the most interesting part. Encoder generates the mean and variance of distribution and resamples the distribution based on the normal distribution. The loss for training consists of two parts. First one is reconstruction error, and we use as MSE. Second one is K-error divergence of assumed distribution of latent space and the real distribution. The beta stands for beta VAE, and it can increase disentanglement. This is our encoder architecture, and we can add pooling layer to increase recipe field and collect global information, which will be very helpful for containing more global information in latent space. Decoder part is just the inverse of encoder without pooling. Here is the most exciting part in our work, reprojection. We simply follow the pipeline of VAE, but at the end, we input the reconstruction image to encoder and get a reprojected latent space. So based on previous loss function, we add one more term. We call it reprojection error, and we can consider it as a regularization term. There is a visualized explanation for this idea. Going through encoder, we can consider this procedure as projecting the original image distribution to latent space. Then we input the reconstructed image to encoder again, like reprojection. What we want is how the model to make these two latent space converge and overlap, just like the figure showing. The evaluation part is quite straightforward. We train our model for one purpose. Different things stand for different latent space. Choose one consecutive image pairs and compute the K-error divergence of the latent space for image 1 and for image 2. The large K-errors D means different scene, and the small one predicts the image pair is in same scene. Here is a diagram of K-error-D examples in several image pairs. The overall performance is based on the accuracy of scene detection. As the first of our tasks, we simply compute error 1 or error 2 distance between consecutive image pair. The figure shown here is one of the top 10 significant scene changes it predicts, which obviously is a wrong one. As expected, this manual method suffers greatly from mirror translation of scene and noise like this. There are some of the results from our model. The top ranking scene changes are mostly correct. Here is our final result compared with other methods. With pooling layer and reprojection, we can find the reconstruction error increases. But meanwhile, the representative learning of latent space greatly increased. Accuracy of our model is promising. Here is our conclusion. We find out scene change detection is interesting but unexplored domain, especially how to do it with unsupervised learning. VAE is an excellent technique, and it can help model learn the underlying distribution of images. Beta VAE is a much more promising one by adding one regularization term to increase the disentanglement. Our idea about the reprojection has great potential to dig into for further publishment. It's behind mechanical theory, also needs explosion. We need to continue our work in the future. Yeah. Finally, our Repro-VAE can learn excellent representative space of images, which has potential in many applications like scene classification, image clustering, and so on. Finally, thanks Professor Raj for leading us into the field of deep learning, and thanks TA Conan for his kind help in our project. That's all. Thank you.